Yes, we are back. So, um, let's continue with the whole thing. Last time we created a simple model, a DNN model, right? A little deep neural network with few layers, with some, I guess, two hidden layers, and also few activation functions I was gonna introduce in this chapter. So, before we go with the activation, let's see what the networks actually looks like without the activations, right? Uh, and let's talk about activation in general, right? It's nothing crazy actually. Okay. So if the model was without any activation, it might look something like this. I'm taking these images from the book itself, and I'm in the GitHub repository. Yeah, this is how the whole thing would look like without the activation. This is the model that we created. Okay, we're gonna explore a little bit of mathematics into of it basically, right? If you remember, we defined the model right here. This is the model, you remember? So there are two hidden layers inside it and one output and a sigmoid layer. Okay, so this is how the whole network looks like. And if you can see, there are 25 of the inputs coming in, and then again you can clearly see it's going into 5 neurons in your first hidden state, and then 3 neurons in your second hidden state, and then comes out the output, right? And you pass the output to the sigmoid function. That's pretty straightforward. I don't need to really tell you what and how that is working, right? Now, if I were to show you the mathematics by hand, it would look something like, okay, just so you know, this guy that is a linear, it is the operation that happens inside it is basically uh, a matrix multiplication, if you want to call it, right? And that looks something like this. For instance, take this. If I were to put all of this into the whole thing, okay, um, it goes like we have a vector of 25 comma 1. Okay, so all the numbers, the x naught to x24, right? So there are 25 input features, right? And we are passing it to that, so it's basically going in here, and it's doing uh, what we call a simple terms. If this is the thing, uh, we have to transpose it. So it's actually, it looks something like this. Give me a second. So this weights are basically these lines. Okay, these lines are representing weights. So it would be like this. Okay, and one line is basically one line is representing one weight. So in this scenario, there are 25 into 5 weights, right? So pretty big one, that is 125 weights are there right inside. So there are 125 lines in between these input and the first hidden layer. Okay. Uh, so now we can represent few things. For example, um, they have represented in the book. It's W00. Basically, it says uh, this guy is in the first layer, and it's the first vector. Okay, and these guys are getting vectors is made up of all these vectors, all these scalars, basically all the lines that are going towards that neuron, right? So it would be something like, um, these are all vectors actually. If you take this, was supposed to be a vector, a column vector with all the numbers here. Some numbers are there, right? um, okay, and then again this is also another vector with some columns, right? Okay, but now what you have to do is you have to stack them up, but you have to stack them up like this. That is 0 0 transpose of the whole thing, then 0 1 transpose, then all the way to 0 4 transpose. And remove this, guys, because these are column vectors. You have to transpose them to row vectors. So if you check this out, this is now 5 cross 25, right? And you are doing a dot product with matrix multiplication in a sense, not really dot product, in with the input layer, that is your 25 into 1. So it would be like x naught to x 24. Okay, so you can see it will give an output of what? Simply it will give an output of 5 comma 1, right? This is the output shape. So those things can be given by 0 0 z01 all the way to z04. Okay, I hope that makes sense. You see these lines right here coming in, that is what it is. And apart from that, now in this in the next stage, what we have is this part is, again I'm writing it down here so we can use it again. Okay, this part comes back. So this is the first hidden layer and the multiplication with the input layers, right? And now we are going towards the second hidden layer. So it goes like what I'm gonna do different color. Okay, z00 z01 z02 z03 z04, and once it's done, we have next set of inputs, that next set of operations to be done, that is from coming from hidden layer 1. Okay, now if you take these things, and I have to do the same thing on this guy, right? So I'm gonna just keep it here for a moment, and let's take the so it will be like 1 0 transpose, this is 2 0 transpose, this is 3 0 transpose, and so now this part, this was size of this is 5 comma 1, now is 5 and here it is basically 3, right? So it will output again a 3 comma 1 matrix, and we are denoting it by what? Z1. So basically this, the first 0 is representing what hidden layer we are from coming from, and the second, so you see it's coming from the first hidden layer. I mean the first hidden layer, this one, and this is the second hidden layer. We're denoting it by from like 0 indexing, that's why. Okay, and cool, that works. Yeah, so it's 1 0 1 1 1 2. Now that's also done. I'm gonna put an arrow here just to for reference that this guy is going here. Okay, okay, now again we have a third guy, right? That is, we take this guy and again keep it here, z10 z11 z12, and do what? Do a simple, we take this guy, this one, and there's only one operation that needs to be done on that. So it's a simply taking 0, that's it would be 2 0 transpose, and that is it. And now this guy, if this guy is 3 comma 1, this is 3 comma 1, and output is simply 1 comma 1, right? I hope that makes sense. And you finally have the final output as a z value, which is simply your z2. Okay, and now this thing will be passed into your sigmoid function. So sigmoid of z2 will go. Now what is formula for sigmoid? I'll draw it in different. Sigmoid's formula is sigmoid of z, sorry, it will be like 1 by e to the power minus z2, right? And this will basically give out one number that is between 0 to 1, so it can be thought of as some kind of probability, right? So that's what's happening here. Okay, that's the mathematics behind it. If you see in the um, documentation as well, I can show you the documentation. Linear. Okay, so here you can see like what is happening. Okay, I can put it here right inside. Okay, yeah, you can see that what's the formula is y equals to x a to the power a transpose plus b. Okay, yeah, and that's what we're doing. We're doing a transpose and we are multiplying it and all that. But our mm, I hope that makes sense, right? So the bias term isn't there yet because we have said that bias equals to false as of now. So let that be. Okay, cool. The whole thing is done, and let's get moving. Now we are going to talk about activations and what they are and why do we need them, you know. So if you think about what is happening here in this scenario is simply we are taking a neural network and we are trying to draw classification in essentially is simply stating we are trying to find uh, let's say we're trying to find what we call a decision boundary between the two classes, right? If there is class 1, class 2, and we want to if we are to show you in a graph, it will be something like this. You have a graph coming in, you have the data points, few data points are here, and there is another data point coming here, and you are essentially trying to find a line that is able to divide both of them. So this is your decision boundary. But what if your line is not separable, right? You cannot separate. We have already talked about kernel methods, I guess. So if what if in this scenario you have a graph just like that? I'm gonna use the same color so that a scenario just like that. Okay, but now the problem with this one is, let's say it's something like this, and the other class is around this like this. Okay, so there's no way I can draw a line here. Now there's no way I can just draw a line on this one, right? That can divide both of them. Only way is to draw a circle around it, right? Only way is to actually draw a circle around this guy to make the decision boundary. So that is the idea that we have. We have to introduce this kind of a non-linearity into data. If your data is not linearly separable and you want some kind of a non-linearity in the and then the lines that you're making right now, it's just making straight lines. Your model is only able to make straight line because think about this. Okay, think about this. Essentially what you have in a lot of affine transformation simply scaling it, and scaling and adding into it. That's it. It does not introduce any new terms into it. For example, I'll tell you. So basically, affine transformation does like rotations and scaling and flipping and sharing. So this function that you're seeing, this function, it is your affine function, right? And I can also give you an example of what that is, right? Now think of a simple network, something uh, something like this. Let's say this is the input values. It's going into a neuron, two neurons. Okay, so it's coming here, and then um, it's, let's say it's going to activation function, all that stuff, and then it's just going to another neuron, one neuron, and that's, we are getting the output out of it, right? So your input is here, your first hidden layer and is there, and this is your output layer, right? uh, Output is there. Okay, cool. Now actually the things that are happening here is pretty obvious and simple to understand. Okay, if I were to actually mathematically do this, so it's basically like saying omega 0 0 omega 0 1 omega 1 0 omega 1 1 into what, x 0 x 1, which is your inputs, x 0 x 1. This is your omega 0 0 omega 0 1 omega uh, omega 1 0 omega 1 1. So now you can see uh, this line, I already showed you this line that we have got is basically these two lines, right, coming into this part, particular block. Okay, so in the previous example we denoted by saying that it is basically 0 of 1 and the transpose of, and we put it like this, right? This is basically, it's all the ones that are going into the first neuron. Okay, yeah, cool. So we were talking about this guy, right? And now we are also introducing some bias here. Let's say biases are also added. Okay, so we have added the bias also, 0 and 1. Okay, so now if you see, this is what we call the linear transformation. So what is a linear transformation? Where you have a one vector. Linear transformation is where you have this one vector that is being transformed by a matrix. This is what we call a linear transformation. So basically it's a matrix multiplication on a vector basically. So you can think of it like that, you know. So that is your linear transformation in an essence. So now if you think in the, I really recommend to go and watch the um, uh, three blue one brown videos on essence of um, linear algebra. So if your vector was here, let's say this x1, this is x1 and x2, huh? So it might happen after all the after changing this, after doing this matrix multiplication, it can do two things. That is, I guess it does, it can scale it, that is it can scale it to some values here, or again go here or something, scale it basically. It can end up here, it can end up here some on the line, or it can rotate it, right? So it can go here and then also scale it. So these things depends upon the values that are here inside the, you know, um, in the matrix. So if you have a matrix of 1 0 0 1, this is what we call identity matrix, and you have a value, let's say 2 comma 2, and you are doing this, it will give you 2 comma 2. So after the transformation itself you are still in the same point. But let's say if you have 1 1 0 1, okay, and you have 2 2, so let's see how that goes, right? So it's 2, so again it will give out two some values like this, 2 into 2 plus 2 into 2, that is 4, and 0 plus, that is what you got. So after uh doing all this, right? I'm gonna remove all these other guys. The transformation is basically x value, it's, let's say it's 2, so it's 4 somewhere here, and the guys, so it's basically here, right? X value is here and 4 value. After transformation, it got to this guy, so it rotated here and also scaled. You see the point that I'm keeping? So that's how it goes. Okay. um, yeah, so this is what we call the linear transformation part. And this whole thing, this damn thing, right here to here, when we're adding the biases, this is called a affine transformation, right? Affine transformation is this guy. Cool. Okay, so affine transformation is simply a linear transformation, such as rotating, flipping, and scaling and stuff, right? So now, in this scenario, what we did first, we used the weights to perform a linear transformation of the features. Here you can see that's what we did here. We did a linear transformation on the features x and x. This column is the feature that we have, such that the resulting feature is rotated. You can see that it's, if weights were this, it would be rotated or something, scaled, or maybe flipped, you know. Then it uses the bias to translate the whole feature space to a different origin. So if you add, let's say if you add this guy also here, this biased term, let's say the bias was 1 comma 0, then yeah, then what happens is simply it becomes 5 comma 2, right? Is some 5 here, the app, the whole uh, the whole feature space is basically translated to a different origin, resulting in a transformed feature space in itself, right? Okay, so that's what it is. There's also one way to visualize the same equation here, as in like this. It goes like x comma x 0 0 0 and x 1 0 and plus x1 0 1 and 1 1. Okay, and plus b naught b1. There's also one way to initialize it. Or if you do this, it's 0 0 x 0 plus 0 1. If you do the actual multiplication of the matrix and vector, so you get something like this, right? X1 plus b1, and that is it, and it's been added with the b naught and b1. So this is, if you see, what is this? It's an equation of a line. I hope you can actually appreciate the fact that this is an equation of a line, and we're just adding one more constant into it. So again, I mean, you already added here, so I don't need to do that. Sorry for that. Yeah, so it's the equation of a line, right? So you are transformed the whole, so you are, these were the features, and you multiplied it with from some numbers essentially, and you added another number to it, so it's again a number. So you are not able to do anything. It's a still it's a line. This is also a line. There's no way you can actually introduce any x square term, or x to the power 3, x to the power something that will make this curve, make this line into a curve, so that is the problem with using a simple deep learning model. In essence, they add zero uh, capabilities of mapping to a feature space that is not linearly separable. Okay, so, and which is in most cases, that's how it goes in real life. These are all dummy examples, so these guys uh, actually get to that. I mean, we are able to do that because we created it, the data set, but in real life you really do not see that, right? uh, okay, that is it. And but now we're gonna create a model with these activation functions. So there are few activation functions that you need to be aware of. Okay, now let's talk about them. Few activation functions, right? The first activation function is the one we already been so familiar with, that is your sigmoid function. It's probably the most famous, I mean the first one and the famous one, because it's used extensively. So what, now you have a way, as I showed you in this picture, if you can see, let's do this, right? Let's do this here, put it here. Okay, now you had the output coming in right from the hidden layer, but you pass this now into another function called the activation function. Now there are many kinds of activation, that's what we are talking about. You can use the sigmoid function. Simply, sigmoid function is this function, e to the power minus whatever the z is coming in. So these z's are coming, so all these guys, you see these guys are going here. So now we are taking this. So I can actually put it much better like this, right? I'm gonna put in different color, minus of omega this guy, and this whole thing becomes what? This whole thing becomes your z, that is your output from the activation function. I'm not writing anything like, it can have some numbers or ij or something. Here also it's ij, right? Something like that in this scenario. And what it does essentially is it introduces non-linearity in your data set. Okay, so the most traditional one among all these is your sigmoid function. Okay, so if you see the figure of sigmoid, so if you remember how sigmoid looked, okay, sigmoid looked something like this. So you had a function that went along. That's a bad one. Let's fix the point where it's into 0.5. Okay, something like this, and it's your 1 asymptotically going there and here as well. Cool. And the derivation of the whole thing, the derivative of the whole thing, it's goes like it's 0.25, it cuts there and goes like it's a normal kind of a thing. Okay, that is what the derivation of this whole thing looks like. Okay, so you are essentially taking all the x, the features. So if you are taking this guy is mapped here, so it will be this like here, right? Ij and x, and this is along the y-axis. So you're taking uh, some value of x and you are mapping it here between 0 and 1, essentially 0 and 1 essentially. Cool, I hope that makes sense. Hmm? Now because of this, there is an exponent function inside it, and because of that there is some kind of a nonlinearity already been inherently introduced in the network. Okay, okay, so why does it matter if the outputs are centered around 0 or not? This is one thing. So you see all these outputs are centered around 0. That is another something that you need to look into, and I encourage you to actually look into it a little bit more. Okay, and let's look into next one, that is, let's say, I think we can go with ReLU or TANH. I guess TANH is pretty, yeah, TANH. TANH is another function. It looks like this: e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. That's all. And the graph kind of looks the same. Only difference being The major difference being it spans from a different one to different one. So for example, it goes, let's say this is your 1 and this is your -1. So now our graph looks something like this. It goes along this and it cuts at a 0 position and goes like this, right? That is it. That's what it is. And the derivative of the whole thing looks something like goes around here like this. So hard to draw a normal curve. Here it hits it here and then all the way back. Whoop. That's all. Okay, cool. Yeah. So tanh function squeezes the input value between -1 and 1. Therefore, being centered at 0, the activation values are already somewhat normalized input for the next layer, making the hyperbolic tangent a better activation function than the sigmoid. So regarding the gradient, it has a much larger peak value of 1, but it decreases even faster, approaching 0 to absolute value of z as low as 3. Okay, cool. We will see into it more when we code it. Okay, let's take the third one. Third one being ReLU. This is another activation function. Okay, just so you know, this is what happening here. These formulas are being used to compute this guy. So here all the z's are basically your this guys, right? Okay, remember that. Now the ReLU part. ReLU is pretty famous. I probably the most used activation function in any network right now, and because they tend to work really nice. So if I were to give it a formula, ReLU of z is nothing but simply max of the z or the 0. It's as simple as that. So basically it's saying is in the graph, if I take a graph right now, you have a graph like this, let's say, and you want to do something about it. So it goes like if the x are positive, that is your x, right? X value in the sense your z value, which is nothing but the product of these guys. These guys are positive in nature, then it's a linear function. That's it. It's pretty simple. If they are positive, then they are all a linear function. But if they are negative, then it's all zeros. That's it. So this is how the whole thing looks like. And its derivative is simply a step function which goes till 1. That's it. Okay, I hope that make sense. Okay, cool. Hmm. Okay, so maybe squishing is not the way to go. What if we bend the rules a bit and use activation function that bends? So in that scenario, what you see here, the main difference here is these guys are squishing. The sigmoid and tanh are mostly squishing the coming input, whatever, into a range of something, right? So here no matter what the value of x that is coming, or omega t, whatever the value, I don't care, as long as it goes to sigmoid or tanh, it will be squeezed into a range of 0 to 1 or -1 to 1. It's as simple as that, right? But here you see that's not the case. If the value of these are positive, if these are positive, then ReLU is linear, so it's not squeezed between any set of um what do you say, any set of limits, right? As if it's not from 0 to 1 or -1 to 1 or something like that. Okay, so we ReLU was born like that. It spawned a whole family of similar functions So the ReLU or one of its relative is the commonplace choice of activation function nowadays. It addressed the problem of vanishing gradients found with its two predecessor, while also being fastest to compute gradients for. So I don't know if you have noticed one problem here. What if, because these guys can be negative, right? I mean, these guys can be negative. If these guys are negative, okay, if these guys are negative, then ReLU, say, it will just give out 0. Think of that. If this output is converted as 0, let's say all of them are 0, here is also 0, this is also 0, 0, 0, then essentially there is no learning happening, because all of them are in a matrix multiplication. If all these guys are 0, then the next part where it will go to these guys, because this will be multiplied with the weights, and these thing will be computed, and this will also become 0. The whole network will become 0. Every single node will become 0. That's also a problem, and this is the problem that can be solved by variants of ReLUs, and we're going to look into those variants. There are the variants are like parametric ReLU, ELU, CLU, a lot of small variation they did. Okay, so do that. So okay, let's so the upside of using ReLU is that its gradient is either 1 for positive value or 0 for negative value, right? Yeah. So as I already showed you, derivative of this, either it is the gradients will be 1 for any positive value, uh, and 0 for any other negative value. So no more vanishing gradients. Vanishing gradients is basically when your gradients becomes too small, 0.000001. This is what we call vanishing gradient. See, everything is happening in computer, right? And computer has limitations when it comes to the precisions of numbers, right? If your number is too small, and firstly there might be a problem in storing it in the whole memory. Secondly, it can also happen that the updates that you make, because of course the new is going from old minus of and the gradients, whatever the grad is there, right? If your gradient is really small, right? Let's say your gradient is 10 to the power minus 5, and this is also mostly we take it as 10 to the power minus 3 or something, right? So essentially they add up to 10 to the power minus 8. That is like minuscule change in the actual uh, parameter. So you see, the training might not happen, that is the conversions might not happen, or even if it happens, you will have to take a lot and a lot of um, epoch and training loops to actually get to the conversion state. So that's also not good, right? That is what we call the vanishing gradient problem, and it mostly happens because if the problem with any number that is between 0 and 1 is that any number, let's say, and you multiply the numbers, any numbers between 0 to 1, it will always give you a smaller number. So it was 0.5 into 0.5 and to 0.5, it will be a smaller number, right? It will be 0.25 here into 0.5, again it will become another one, 0.125. So you see, this is a way smaller number than the individual numbers, right? So that is the problem that we have. So with every iteration we are multiplying, if these smaller numbers over and over again, then we have this problem that the gradient is so small that it's almost negligible, and it does not do any kind of training whatsoever. That is the vanishing gradient problem, and ReLU kind of solves it, because it has a way to either keep the gradient as 1, or it will keep the gradient as 0. For positive value it's 1, for negative value it's 0. That's how simple it is. This pattern leads to a faster convergence in network. So really it leads to a faster conversion network. However, this behavior can also lead to what we call the dead neurons. So that is what I just explained you. Dead neurons is what happened here when every single one of them had negatives. So, okay, that is a neuron whose inputs are consistently negative and therefore always have a activation value of 0. Worse yet, the gradient is also 0 for negative inputs, meaning the weights are not updated. It's like neurons are stuck. So basically, if this happens, then the whole network is dead. You can't do anything about it, no matter how much loops are you running, right? So the activation value of ReLUs are obviously not centered at 0, of course. Does it make it worse than hyperbolic tangent? It surely doesn't. Otherwise, it would not have become such a popular activation function. And a lot of practitioners use ReLU as their default activation function. With a comparable, so the ReLU with its comparably larger gradients is able to achieve better and faster results than other two activation functions, despite the fact that its outputs are not centered around zeros. For deeper and complex models, it may become an issue commonly known as internal covariance shift, which is just a fancy for there being different distribution of activation values in different layers. Okay, I think it's a little out of the scope of this discussion, but yeah, but this can be solved using like normalizations and layer normalization or batch normalization, group normalization, all that stuff. Okay, cool. Okay, we will look into how the implementation happens in some time. Okay, now there are two, three things. There are now only thing that you have to look into is the variants of ReLUs, that are the leaky ReLUs and all that stuff. So the fourth one is leaky ReLU. Okay, is this essentially looks like the same thing as goes like this, but instead of having like this, it eases it out here in this part. In the negative part, it does not make it complete 0 because we don't want the dead neuron problem. So we will ease off this part and then it goes same. So that is it. So what it does is, uh, if you think it, the equation would look something like this. Z is equals to max of 0 comma, that is there, but we are also adding a small number plus the minimum of 0 comma z. So even if this becomes 0, this guy becomes 0, that is if the z is negative, then this whole thing becomes 0. We will all have a small value here. Okay, I hope that makes uh, sense. Okay, or you can visualize it like this also. Okay, you can go like, say it's something like this, where it's 0 if z, if x is greater than equals to 0, or it is 0.1 to z if x is smaller than 0. X or z, whatever you call it. I'm calling it, I've been calling it x for some reason. Okay, okay, as you can see in the figure, that the leaky ReLU is pretty much as same as the ReLU, except for the tiny barely visible slope on the left hand side. Basically this part, right? This part is where the magic happens. Cool. Hmm. Okay, that is it. Then we can also have parameterized ReLU. In this case, we uh, added this 0.1, 0.01, right? We can make it into a parameter. We can just say that what do you do? Take the whole thing, but change it into a. This is something you can change over time if you want to. So that's your parameterized ReLU. Right, okay, that's it. There are other ones also, silu, ilu. So it looks something like, I'm just give you a small brief into it. So it might look something like this: smooth curve, and then it goes like this, and you can change it also. How is this curving, right? Something like that. That's also there. Silu, ilu, I forgot the full form of them. Yeah, but yeah, these form of activation function also there. That's a variant of ReLU. Okay. Okay, I guess I have made all that stuff very clear. Let's find out what we can do here in this case. Okay, let's do this one by one. Hmm? Okay, let's draw this. Yeah, the sigmoid function, as I said, as I already showed you. And let's create a dummy tensor and pass it to sigmoid function. What do you get? You take, see, there was -3, 0, and 3. Now we have squished it into 0.5. You see, for the 0th value, it's 0.5, right? And for -3, it is somewhere around 0.04. And for +3, it's somewhere around 0.95. So that is there. I hope you can see this actually. Let's get it here. Yeah, that is done. And we can also draw, okay, we can use it. We can also use the nn function directly like this, and it does the same thing. Okay, either you go a torch sigmoid or nn.sigmoid function and then pass in the so it's basically callable. Okay, then let's talk about tangent. It looks something like this, right? It goes from -1 to 1. The gradient goes from 0 to 1. Okay, and let's take a dummy example, and that is how it looks. Here you see -3 is giving a very negative value, and +3 is literally the opposite of that. Here is not the case because it's going from 0 to 1, right? And also you can use the nn.tanish to do the same thing. Works. Now the ReLU part. ReLU looks something like this. You can see how it's the graphs are. And let's take these two guys and see. For 0, it's 0. For negative, it's 0. For positive only, it is positive. That is linear, right? And we can do the same thing using nn. Okay, and clamp is also, the clamp is basically clamp out everything that is not, that is lower than 0. That can be also a way. Okay, now the leaky ReLU. Let's say leaky ReLU. See, you see the black line, you see the minuscule gap there. I mean, difference between them. It's not overlapped, the green, the red line and the black line. That's the reason. That's where the leaking is happening actually, on the left hand side. Okay, let's create one, this guy, and you see, instead of giving, so here 3, instead of giving 0 here, it gave a value that is very close to 0 but not 0 for negative values. Cool. And you can use nn to do that again, but here I think there's a difference in, okay, you can tell the negative slope. So if you can tell the negative slope, basically it can be also be treated as the parameterized ReLU, right? Because that is your negative slope. Okay, for example, if I do it, let's say 0.1 or something. Oh, that's, see, there's such a big leak is happening basically, you know. Okay, parameterized ReLU, brought it out. Okay, here you see it's much bigger in this scenario. Plot, we are using preLU from F, and this is what we got. We can use this also to do the same. Let me just check if I do 0.1, what will it give? Yes, it gave the same answer. You see the leaky ReLU with the negative slope value 0.1 and the parametric ReLU with that initial whatever, that is basically the slope. It gives the same values. So leaky ReLU can be used as a parametric ReLU if you want. Okay, so now let's build a model, an architecture with these activation functions inside them. Okay, so here we go. You have this whole model. Okay, there we go. Okay, so now this is what we saw in that figure, right? In that figure here, where was the figure? Yeah, this is the figure, right? This figure. Okay, 25 inputs coming in, 5 neurons in the first layer, 3 neurons in the second layer, and then 1 output out of it. And we are adding now after every single layer. If you check, after the first layer we have a ReLU, after the second layer we have a ReLU, after third layer we have straight away the output as a sigmoid, right? Cool. Okay. We created it. I think we are done with that. We can also initialize the optimizers. Done with initializing the optimizer and the loss function. Let's train the model, and it's training. Yeah, the training is done. Let's plot it. Oh, that looks absolutely beautiful. I hope you can see how good this is, right? Comparing to these guys. Look, it didn't really converge, right? 5 to the 0.5 is the loss that we got here, right? 0.5. And let's see what loss we get here. It is 0.2. Cool. And training and validation. Cool. We got a really good result out of when once we introduce activation functions into it, right? Okay. And when did it reach? So 20 epochs. By 30 epochs, we are almost done actually. Here, let's see. Uh, okay, it's around same in this scenario. It's around the same time. They are also converging, but not the best convergence, right? You might also find that because of this, you might need less epoch also. Okay, keep that in mind. Okay, so if I do the model ReLU dot state dict, and I do this, you can see the weights of the whole thing. And okay, I guess that is optimizer. Can I do something with that? Optimizer ReLU dot state dict. Yeah, all the things that are here is here, I guess. Can I use what happens if I do this? Okay, okay. Where can I find the loss exactly? Do I have the loss function? No, we don't. I never had a opportunity to look into loss. Loss. Somehow can I do something with it? Can I do state dict can be done on loss? No, it doesn't work like that. Can we get the item out of it? Something? No. Eval, forward, a lot of stuff happening. Parameters. Let's try this. Nope. Doesn't work. Okay, let it be. So that is that. And let's put everything together is basically one big thing to do all of it at once. We have already gone through that. So that's it for this live stream. And we'll continue with the next one.